This is the last video regarding the interdisciplinary course on economies of scale. In this video, we will deal with Amdahl's law. Amdahl's law regulates speed up. Now let's see what that's about. As the number of processors in multiprocessor systems increases, it is quite obvious that any modern computing system inherently strives to achieve the absolute maximum possible processing power available. Consequently, adding multiple microprocessors is one of the most effective and reliable methods that can be followed to successfully obtain this significant increase in computational power. However, even in this specific case, when we are faced with the persistent and common idea that by constantly adding more and more microprocessors to a system, one inevitably gets a speed up, that is, a speed, or rather the specific ratio between the normal baseline speed and the speed achieved with n processors, that is ever higher and higher, in reality, this simply does not happen. This is because there is a limiting effect, a significant effect that requires an amortization phase, exactly like the concept of economies of scale in economics, where initial fixed expenses are gradually amortized over time. So let us take a closer, more detailed look at exactly what the core terms and the underlying issues are in this particular scenario, and why this theoretical model fails to hold up in practice. We have a sequential computation time, which is that of the system when only one microprocessor is running. A parallel computation time when we can use n, let's say n microprocessors, the number below. Actually, it might seem at first glance that we simply divide the number of, we divide the time taken by the number of microprocessors and we get the parallel time. It's not that simple because the processors have to be launched. Essentially, you need to load the program data onto the n-1 processors that are different from the master. There is one that starts all the others. This time is dead time. If this dead time, as we will see, is negligible compared to all the rest of the computation time, we will have the ideal trend. However, more realistically, we must take into account the effect of this dead time. It will be a bit more complex compared to what we saw in the previous videos, but we will see that in this case too, we will have an amortization of this dead time as the number of processors increases. In this case, the parameter of interest is the number of processors. Now let's define these last two parameters. The sequential computing time fraction is defined as the unavoidable amount of time relative to the total execution time during which only a single microprocessor is actively running. For instance, this often occurs during critical setup phases, such as when the system needs to load essential data and programs onto the other available microprocessors before parallel processing can truly begin. So the parallel time we can obtain is given by the sequential time for the sequential fraction, for the sequential time fraction, multiplied by what remains the rest of the time, a parallel fraction. And in that case, we can divide by n, because at that moment, we will have n microprocessors running. So the parallel fraction, as we said, is equal to 1 to the totality of the time minus the sequential fraction. With all these definitions, we can now go on to calculate what this speedup is. The speedup is essentially how much faster our system goes as the number of processors we put into the system varies. For example, the sequential time, the calculation time with a single microprocessor divided by the parallel time, which is the calculation time with n processors. We have seen, however, that we can also express the parallel time as the sequential time multiplied by the sequential fraction plus the parallel fraction divided by n. We need to simplify the sequential time, and we obtain this expression where we see that there are only pure numbers. Time is no longer there. Therefore, the speed up is a number. We have 1 divided by the sequential fraction plus the parallel fraction divided by n. This can be written in many different ways. We can, let's say, go directly to the final one, and we write it by multiplying the numerator and denominator by n. We will have r parallel fraction n times the sequential fraction. N in the numerator. Let's observe what happens. In ideal conditions, the microprocessors all start immediately, and therefore we don't have this sequential r. Sequential r is 0, parallel r is 1. If we substitute, our speedup becomes directly n, which is the ideal one we expect. In real conditions, however, we must take into account the fact that it takes some time to start the other n-1 processors, let's say. So we can make an approximation and say that the sequential fraction is equal to a very small positive numerical constant, which we call alpha, multiplied by the number of processes. Here is the idea always to let's say the idea to simplify. And the number of processors makes it grow. With the number of processors, the time needed to start them up also grows proportionally. So a linear hypothesis, a simple hypothesis. Our R is sec, our sequential fraction will be equal to alpha n. At this point, our parallel fraction will be 1 minus alpha n. Let's look directly at these last expressions. So instead of R parallel, we write 1 minus alpha n. Instead of n times R sequential, we write alpha n squared. So we have this functional form that contains a squared power in the denominator. Now we can also qualitatively understand what happens. Initially, given a rather small alpha, if n, the number of processors, is also rather small, what dominates is the 1 compared to the other terms, and therefore we have a more or less linear trend. However, as the value of n continues to increase, these specific factors become significantly more important, and we will eventually observe an arched trend that clearly features a distinct maximum point. So, what we can effectively establish here is that once the alpha parameter is fixed, and once the specific percentage of time relative to the total calculation that we absolutely need to initiate the system is fixed, and it is important to note that this is clearly a form of dead time. Well, once this specific time interval is firmly fixed, we can then proceed to analyze what the maximum value of n is, and furthermore determine exactly what the maximum speedup we can realistically achieve is. We will soon see that there are some truly interesting things to uncover in this analysis. Now, to calculate the maximum, we perform the usual operation. We calculate the derivative of this function with respect to the variable n, obviously considering alpha as fixed, and then we set the derivative equal to 0. We obtain that the maximum number of processors for a fixed alpha is given by the square root of 1 over alpha. Obviously, it is an approximate value because n must be an integer, while the square root of 1 over alpha is not necessarily an integer. But we will choose values perhaps in such a way that this approximation can be neglected. And S maximum, the corresponding maximum speedup value, is also obtained from this little formula. Let's see what happens. This is what happens. If we assume that alpha is 1/100th, that is, it takes 1/100th of the time to start the whole system of actually a single processor compared to the total computation time, we find that the maximum value is obtained with 10 processors. However, the maximum value is not as high as we expected, equal to about 5. Just substitute alpha into these formulas obtained for n maximum, and you can see that the maximum speedup value is 5, not 10. So here is a graph that helps us understand this trend a bit. If we have an ideal situation, as we add microprocessors, we get a speedup that grows linearly. If we have a real situation, or at least with this slightly more refined model, we see that our computing speed doesn't increase that much, up to 5, and it even starts to decrease. There you see a dampening effect, which in this specific case is a bit more complex, and it actually partly repeats the fundamental things we previously discussed regarding economies of scale. Up to a certain point, we certainly have a distinct advantage in adding new processors to the system. However, as we continue to scale up, that advantage begins to diminish, illustrating the nuanced trade-offs we must carefully consider when optimizing performance in these complex environments. After that, we no longer have an advantage. The only way to obtain a greater speed up would be to decrease alpha and load faster to get the system started faster. Okay? All right, with this, we can wrap up. We hope this will be a starting point for your work, and we'll see you another time. Goodbye.